we begin our discussion on forecasting. Forecasting essentially deals with estimation of future demand for a product. For example, we could have demand for a particular product, let us say in the last 6 years as 25, 32, 24, 28, 26 and 27. The product could be anything, the product could be an automobile, a product could be phones, a product could be machinery and so on, and these numbers could be in multiples of 1000 or multiples of lakhs and so on. For the sake of illustration, we will take these 6 numbers. We can assume that this is the sale in 2009 and this is the sale in 2004. So, the data for the 6 years starting from 2004 to 2009 are available, and let us say for the sake of illustration that these are the values. Now, we want to estimate the demand for the year 2010 say, and which I have indicated by a question mark. This demand estimation is extremely important because this demand estimation is the starting point of production planning, as we saw in the last lecture. Only when we have the forecasted value of the demand, we will be able to make both capacity planning and production planning. So, the whole area of production planning begins with the forecast. So, we will spend time on learning forecasting models. So, we will start with these 6 values as values of demand, and we will try to forecast for the next period. Now, whenever I pose such a question and give 6 values of demand and ask a class of students to make their own forecast, I normally get several answers that the students give, and let me write down some of them on this board and then try to explain them one by one and lead to the various basics and principles of forecasting. So, let us consider these 6 values of forecast, and let us say these have been given by 6 different people. Now, when I asked the students the basis or the reason behind which these numbers were given, I got a variety of answers. So, I will write down these answers and then we will slowly see the relevance of each one of them in the context of forecasting. So, the first f is equal to 27, forecast equal to 27 comes from simple average. So, one of the students believes that a simple average of these 6 numbers adequately represents the forecast, and we add all this and divide it by 6, we get f is equal to 27. Another student said that he was interested only in the last 4 values, and this student felt that the first 2 values were little old, and therefore, he is not keen on considering these 2 values. He believes that the last 4 values adequately represent what is happening, and the value and the average of the last 4 values turns out to be 26.25. A third person said that the forecast could be 28, and the third person reasoned out this way by saying that there is an increase and then a decrease and then an increase and then a decrease and then an increase, and so the estimate after the decrease happens to be no, the third student who said 28 started by saying that the student looked at the last two values which happened to be 26 and 27, and the student believed that considering only the last two values, this seems to show an increase, and therefore the student gave forecast as 28, which is an increase based on the last two values. Another person looked at these values and said that the forecast could be 30. If we assume that, or if we consider that this data corresponds to sale of automobile, and this person believes that the sale of automobile is related to the population in that area and is also related to the buying power of the population, and the person believes that due to increase in buying power of the population, the demand is expected to go up from its last values, and therefore the person estimated that 30 is a very good forecast for this for the year 2010. So, this is based on other factors. Now, this person who gave forecast equal to 26 believed that there was an increase and a decrease. So, it shows an increase and then a decrease and then an increase and then a decrease. Now, there is an increase and the person expects a decrease and believes that the value 26 comes from decrease and increase, increase and decrease. Now, this person who gave forecast equal to 27 took the last three values instead of the last four and said 28 plus 26 plus 27. So, this is the average of the last three. The person who gave 26.833 also considered the last three values, but believed that since this value is the oldest among the three, this is older and this is the most recent value, the person gave weights and said this is going to have a weightage of 1, here there will be a weightage of 2, and here there will be a weightage of 3, which is the closest. So, the forecast would be 1 into 28 plus 2 into 26 plus 3 into 27 divided by 6, which gave 26.833. So, it is a weighted average on the last three values. The last person who gave value equal to 26 felt that if you look at all these values, 32 seems to be an outlier and there could have been some assignable reason for this 32, which looks like a spike. So, the person took away this 32 and then found the average for rest of them. So, this is remove 32 and find the average. Now, let us look at each of these 8 answers and more importantly the reasons associated with these answers and try and learn some aspects of forecasting. Now, this is centered around the average, which is a measure of central tendency of this data. This is also centered around the average, even though smaller or less amount of data and more recent data has been considered. This has a slightly different assumption, that this is based on the increase that happens here. Here the person has considered other factors. Here also the person has considered an increase and decrease. This is based on the average. This is also based on some kind of a weighted average, and this removes the outlier. So, let us say out of these 8 different reasons given, 5 of the reasons are centered around the average in some form or the other. But if we look at this data and before we start making any forecasting, we need to understand whether this data actually represents a constant or what is called a level, or whether there is some kind of a trend that is happening. So, if we look at these values, in some sense we do not see a clear increasing trend from this to this. We also do not see any kind of a decreasing trend. So, I am going to assume that this does not show any kind of a trend, and therefore, I am going to start developing models only for level or what I call as a constant model, which in some sense has been validated by 5 out of the 8 people saying that it is centered around the average. So, essentially we are trying to find out a constant or a number which adequately represents all these numbers under the assumption that there is no increasing or decreasing trend. So, which simply means we are trying to fit something of the form f is equal to a, where a is the constant or the level that we are trying to find out. But then we also understand that if this were to represent a constant, then why do we have these variations in these values and not the same constant that comes as a forecast? The reason behind is there is a certain inherent variation or inherent variability in the system, which we call as some epsilon, and this epsilon is the noise or inherent variation or variability in the system, and this noise is expected to have parameters 0 sigma square, which means this noise has a mean of 0, which also means that these inherent variation or statistical fluctuations will cancel out as time passes, and these variations are small because their variance sigma square is also assumed to be a very small number. So, if we make the assumption that this represents a constant and we are trying to estimate that constant a here, now we will try to find out various ways of estimating the constant. So, the simplest and the best way to estimate the constant is by looking at the simple average, which the first student actually mentioned as the forecast. So, simple average is the simplest and the easiest way to give a forecast for a set of data which shows level or which represents a constant. But when we take the simple average, we also assume a few things. Number one is we are considering all the data points and we are not leaving out any of the data points. Second is we give equal weightage to all the data points. So, under these two important assumptions, that if we consider all the data points and then we give equal weightage to all the data points, we get simple average to represent the forecast of this. So, if we make a decision based on the simple average, we would say that the forecast for 2010 is 27. It also means that the forecast for 2011 right now is 27, because if we add a 27 and then take the average, we will get the same 27. So, the forecast made here for every period is the same, and that will be 27. Now, the moment we assume that we are going to give equal weightage to all the data and consider all the data, then the question of whether this data, which is 6 years old, is equally important as this data which is 1 year old. So, we need to answer that question, and that makes us move towards what is called a weighted average. So, we can give some weights to each one of these and then compute a weighted average. For example, if we give weights W1, W2, W3, W4, W5 and W6, then the weighted average will be 25 into W1 plus 32 into W2 plus 24 into W3 plus 28 into W4 plus 26 into W5 plus 27 into W6 divided by W1 plus W2 plus W3 plus W4 plus W5 plus W6. And as long as the W's are greater than or equal to 0, we would get an answer which is within the range of 26 and 32. It is also customary to define the W's such that sum of the W's is 1, so that the denominator is 1 and you do not divide it by the sum of the weights. So, a weighted average is as good as a simple average. It has the additional advantage that we consider all the points as in simple average, but we are able to capture the relationship that more recent pieces of data add more value to the forecast, and therefore they are given higher weights, or there is a possibility to give higher weights to more recent data, so that the effect of the more recent data can be captured into the forecast. The obvious disadvantage of a weighted forecast is how do we determine the weights. One person may want to give weights 1, 2, 3, 4, 5, 6, another person may want to give weights 1, 1, 2, 2, 3, 3 and so on. So, for different weights we have different values of the weighted average, and it is not perhaps possible to find out a consistent set of weights or a value that comes out of a given set of weights as acceptable to a group of people. But if a group of people sit together and say that this in our opinion are the weights W1, W2 to W6, then the weighted average can be a slightly better estimator than the simple average. Then we move to the next idea that was shown here, where the person had taken the average of the last 4 values. So, there are 6 values, but then somebody had decided that the first 2 values being very old are not going to be as important as the last 4, and therefore the person has taken the last 4 values and computed the average. So, the average of these 4 becomes 26.25. So, when we leave out certain data points and consider only the last k data points, then we develop what is called a k period moving average. It is called a k period moving average. So, the 4 period moving average gives us a forecast of 26.25. A 3 period moving average taken here gives us a forecast of 27, which is the average of 28, 26 and 27. So, moving averages essentially are made, or decisions based on moving averages are essentially made by assuming that the last k periods are more relevant and the others are left out. So, a k period moving average can be thought of as giving weights of 0, a 4 period moving average can be thought of as giving weights 0, 0, 1, 1, 1, 1. So, every moving average can be thought of as a weighted average with weights given correspondingly. A 3 period moving average can be thought of as giving weights 0, 0, 0, 1, 1, 1 and it becomes a weighted average. While moving average is able to capture the principle that more recent points are important, the older points do not contribute much, then there are 2 issues that are associated here. One is, do we essentially ignore all of them? After all, do not they add a small amount of value, which perhaps could be modeled or could be taken into account by giving slightly smaller weights. But then as we keep increasing the k, for example, a 4 period moving average gave 26.25, a 6 period moving average for this data would mean that you are taking all the 6 data points, and a n period moving average, if there are n data points, will be the simple average itself. So, moving average is related to simple average, it is also related to weighted average. So, this is another form of average, which is the moving average. A 4 period moving average is shown here, a 3 period moving average is shown here. The next thing that we can look at is, so if we have a simple average and a weighted average, can we have something like a weighted moving average. So, a weighted moving average is shown here with 26.833, which was obtained by considering the last 3 points, but giving differential weights of 1, 2 and 3. The oldest has a lesser weight of 1, the middle one has a weight of 2 and this has a weight of 3, and the weighted 3 period weighted moving average gave us 26.833. So, we have seen 4 different forms of average: the simple arithmetic average, the weighted average, the moving average and the weighted moving average. All 4 of them are measures of central tendency. All 4 of them would give us values which is well within the range. Now, I also need to explain the reasoning behind these other 3, and also we need to try and position the other 3 reasons in the broad context of forecasting. Now, when we look at these values and when I introduce these values, I said these would represent the demand of a particular product, and the only thing that we have right now here is that how the demand behaves with respect to time. So, the behavior of demand with respect to time has been captured in this data, and all data where the demand is given with respect to time come under the category of time series models or time series forecasting. So, this is an example of time series data where the behavior of the demand with respect to time is provided. Now, when we start looking at this f is equal to 30, now here the person who said f is equal to 30 assumes that there is a relationship, there is some other factor which is influencing the forecast, and that factor could be the buying power of the people and so on. Models where other factors influence the forecast are called causal models, where there is a cause and effect relationship between the forecasted variable, which is the independent variable, which is the dependent variable, and the causal variable which becomes the independent variable. So, even though this is a reasonable value, the thinking process behind these value comes from the assumption that there are other factors, and that leads to other type of forecasting models. Right now in this lecture we are restricting ourselves to time series forecasting, and much later we will see a couple of models for causal forecasting. So, that is how one can explain this other factors. Now, there are 2 other answers which need an explanation. Now, both of them are centered around the belief that this data is not stable and flat, this data shows a certain increase or decrease, which essentially means that in both these instances the person believes that there is a trend, and here also there is a trend. The rest of them, based on averages, do not believe that there is a trend. So, once again time series models have different classifications. Now, the first ones are called only level models or constant models, which for example was the assumption when somebody made this forecast, when somebody made this forecast, when somebody made this forecast, this forecast. Whereas, when someone gave this value, which is f is equal to 28, which was based on an increase, and f is equal to 26, which was also based on increase and decrease, there is an assumption here that the data is exhibiting a trend, a noticeable increase or decrease which cannot be attributed to randomness or noise. So, there are trend models which we will see a little later after we address this particular model called the models for data that exhibit constant. So, the last point that requires a certain explanation is this. Now, this person said, if I look at these, I find that this is an outlier. So, I am removing this and then I am trying to take the average. So, the general assumption is that this person believes that this data represents a constant or level data. Person assumes that there is no trend or anything, except that the person believes that this number seems to be slightly high and perhaps may not be adequately justified by the assumption that it is a noise. So, in such cases it is also customary to remove certain pieces of data after the analyst is fully convinced that this may not actually contribute or it might take away. So, in such cases you remove a piece of data and then you find the average. So, these represent different kinds of thinking, but largely centered around average, which represents that the assumption behind here is that it represents a constant or a level model, and whatever variation we have is attributed to noise or statistical fluctuation, and we are trying to forecast f is equal to a plus epsilon, where epsilon represents the noise or the variability, and which has a mean of 0 and it has a variance of sigma square. Other things such as trend models and other causal models we will see as we move along. Now, let us look at one more thing. Let us look at these pieces of data once again. Now, if we look at the 4 models that we have seen, the arithmetic average, the weighted average, the moving average and the weighted moving average, all of them have advantages and perhaps a little bit of limitations. The arithmetic average gives equal weights to all the points, which we may kind of question, because it's only customary to believe that more recent data should contain more weight and are more important. The weighted average has the disadvantage of not being able to arrive at some kind of a consensus weight or an acceptable weight. Moving averages are very nice, but moving average tends to ignore or give 0 weight to earlier points and so on. Any weighted model has the limitation of getting the right kind of weights. So, it now boils down to another question: is there a model where we actually consider all these points, we give progressively increasing weights to more recent data, and the weights seem to come logically and are acceptable to everybody? Now, such a model is called the exponential smoothing model. So, let me write the exponential smoothing model here. It is called the exponential smoothing model. Now, let us look at the 6 pieces of data: 25, 32, 24, 28, 26 and 27. Now, the exponential smoothing equation comes from f t plus 1 is equal to alpha dt plus 1 minus alpha into f t. I am going to follow this notation for some time, where f represents the forecast, and d represents the demand. Alpha is called a smoothing constant. Called a smoothing constant. Now f t plus 1 is the forecast for period t plus 1. So f t plus 1 is forecast for period t plus 1. dt is the demand in period t and f t is the forecast for period t. Now in this notation, this is D1, D2, D3, D4, D5 and D6. D6 is the most recent demand, D1 is the oldest demand. Since we know the demand for 6 periods up to D6, we are interested in forecasting the demand for the 7th period. So we are interested in finding out F7. Once again, let me repeat that I am using this notation f t plus 1 is equal to alpha dt plus 1 minus alpha f t. I am defining f t plus 1 as forecast for period t plus 1. There are other notations possible. Right now it is a bit too early to describe other notations, but as we move along at a suitable time, let me compare this with other notations and explain the significance of this notation. But let us proceed with this notation. So we are interested in F7, which is the forecast for period 7, because we know the demand up to period 6. So based on this, F7 is equal to alpha D6 plus 1 minus alpha F6. Now we can write F6 as alpha D5 plus 1 minus alpha F5. So F6 will now be written as alpha D5 plus 1 minus alpha F5, and proceeding further we can write F2 is equal to alpha D1 plus 1 minus alpha F1. Now we know D1, right now we do not know alpha and we do not know F1. Now if we assume, let us assume alpha equal to 0.2, alpha is called a smoothing constant and alpha is a number between 0 and 1. So let us assume alpha equal to 0.2. We also do not know F1. So if we know F1 or if we assume a value for F1, then we can use this to compute F2, and then we can substitute F2 somewhere here and find F3. Similarly, use F3 to find F4, F4 to find F5, and then once F5 is known you can find F6, and then once F6 is known we can find F7. So let us simply do these calculations first, get the value of F7 and then try to explain a few things. So let us assume that F1 is 27, which is the simple average. So if we use F1 is 27, D1 is 25, alpha is 0.2 and calculate, we will get F2 so F2 becomes 26.6. Now F3 is alpha D2 plus 1 minus alpha F2, which is 0.2 into 32 plus 0.8 into 26.6, and this on calculation will give us F3 equal to 27.68. Now F4 is equal to alpha D4, F4 is equal to alpha D3 plus 1 minus alpha F3. So F4 is 0.2 into 24 plus 0.8 into 27.68, and F4 will become 26.944. F5 is alpha into D4 plus 1 minus alpha into F4. So it is 0.2 into 28 plus 0.8 into 26.944, and F5 will become 27.154. phi 2. F6 is 0.2 into D6, F6 is 0.2 into D5 plus 1 minus alpha into F5. So, it is 0.2 into 26 plus 0.8 into 27.15 phi 2, which would give 26.92416, and once F6 is calculated, F7 is alpha D6 plus 1 minus alpha F6, 0.2 into 27 plus 0.8 into 26.92416. So, F7 will become 26.94. So, F7 is the forecast for period 7. Based on this exponential smoothing model, we have calculated the forecast for period 7 as 26.94. This 26.94 is calculated based on two assumed values. One is alpha equal to 0.2 and the other is F1 is equal to 27. Now, this 26.94, if we start comparing with these, it is very close to the simple average of 27, and it is slightly far away from a weighted average of 26.833 if we consider a weighted moving average on the last 3 values. Now, what are the advantages of exponential smoothing and what are the areas we need to address in exponential smoothing? So, first let us address perhaps the advantages of exponential smoothing. Now, when we set out to do exponential smoothing, we said that we want a model where we use all the values. Now, we have used all the values, we have used D1, D2, D3, D4, D5 and D6, we have used all of them, and we also said that we should give progressively increasing weights to more recent data. Now, let us see how we give the progressively increasing weight to more recent data. Now, in order to do that, so let us write F7 as alpha D7 plus 1 minus alpha F6, which will be alpha D7 plus 1 minus alpha into, now F6 can be written as alpha D6 plus 1 minus alpha F6, alpha D, F7 is equal to alpha D6 plus 1 minus alpha F6. So, alpha D6 plus 1 minus alpha into alpha D5 plus 1 minus alpha F5. This on simplification will give alpha D6 plus alpha into 1 minus alpha D5 plus 1 minus alpha square F5. Now, F5 will be written as alpha D4 plus 1 minus alpha F4, and if we continue to do this, we will get alpha D6 plus alpha into 1 minus alpha D5 plus alpha into 1 minus alpha square D4 plus etc. plus alpha into 1 minus alpha to the power 5 D1 plus 1 minus alpha to the power 6 F1. So, this is how this will expand to this if we keep inductively substituting the values for this F. Now, if we look at this expression, what we have calculated as 26.94 here can also be calculated in a single pass by using D1, D2, D3, D4, D5, D6 from these values or from these values, using alpha equal to 0.2 and using F1 is equal to 27. Now, if we start looking at these terms, each term uses the demand d and is multiplied by a number. Here it is alpha, it is alpha into 1 minus alpha, etc. So, this can be treated as a weight associated with this demand. Now, I already mentioned that when we took alpha equal to 0.2, I already mentioned that alpha is called the smoothing constant and alpha is the value between 0 and 1. So, 1 minus alpha is smaller than 1. So, alpha here, alpha into 1 minus alpha is smaller than this weight, this is smaller than this weight, and so on. So, we have progressively decreasing weights from the more recent data value, which is 27, to the past. So, 27 has a higher weight, which is alpha, which itself is less than 1. 26 has a weight smaller than alpha, 28 has a weight smaller than this, and so on. So, if we leave out the last term, the exponential smoothing is a weighted average. It is a weighted average of all the demand points with progressively decreasing weights as we move past or as we move backwards in time. But we also know that if we have a weighted average, then we have to divide by the sum of the weights. So, let us find out the sum of the weights. The sum of the weights are alpha plus alpha into 1 minus alpha plus alpha into 1 minus alpha square plus alpha into 1 minus alpha to the power 5. Now, if we look at these sums, this is one term, this is one term, this is one term, and so on. Now, we know that each term is multiplied by a 1 minus alpha. So, it is a finite geometric series. Sum of terms of a finite geometric series is a into r to the power n minus 1 by r minus 1, if r is greater than 1, and a into 1 minus r to the power n by 1 minus r if r is less than 1. Now, if we make an assumption that n is large, here we have n equal to 6, we have 6 demand points. So, if we make an assumption that n is large, then this will be alpha, alpha into 1 minus alpha, alpha into 1 minus alpha square, and so on. This will become n or n minus 1 as the case may be. But if n tends to infinity, we get an infinite geometric progression with first term equal to alpha and common ratio equal to 1 minus alpha. So, sum of an infinite geometric progression is a by 1 minus r. So, that will be alpha by 1 minus alpha, which is 1. So, as the number of terms increases, this will converge to 1, and even within a reasonably small number of terms like 6 terms or 7 terms or 8 terms, whatever be the value of alpha, the sum will be very close to 1, and therefore, this is like a weighted average where the denominator, which is a sum of the weights, is 1, and therefore, we do not divide. But then we also have a term like this 1 minus alpha to the power 6 f1, and if n is large, this term is 1 minus alpha to the power n into f1. Now, as n is very large, 1 minus alpha to the power n tends to 0. If alpha is smaller than 1 and n is large, 1 minus alpha to the power n tends to 0, and this can be ignored. So, the exponential smoothing is like a weighted average, which is what we wanted. We wanted to use all the terms, we are using all the demand terms. We want progressively decreasing weights as we move to the past, or progressively increasing weights for more recent data, which is what is happening here. Sum of the weights adds up to 1. the last term tends to 0, so it is like a weighted average that we have. And what is also interesting, that given a value of alpha, we get progressively decreasing weights, which in some sense can be accepted by everybody, provided everybody accepts the value of alpha. So, for a given value of alpha, we seem to be getting a very nice and consistent set of weights which also add up to 1. So, exponential smoothing meets all our advantages, or all the things that we expect from it, which is use all data points, give progressively decreasing weights to older data, and have a consistently acceptable set of weights. So, which is what exponential smoothing does. Plus the fact that this weight is very small, 1 minus alpha to the power n is very small, even for a reasonable value of n. So, the f equal to 27 actually does not impact the final answer significantly, because the weight associated with this f1 is practically 0. Therefore, the initial value of forecast can be taken as 27, which is the simple average. Sometimes people would take the last of the values as f1, which also happens to be 27 in this case, but then even if we take 26.5 or 26.35 or whatever, as long as it represents adequately another measure of central tendency or average, the effect of this f1 is not very high. So, in a way we can say that f1 equal to simple average can be accepted, but we have to spend a little more time on this alpha. Now, first of all, alpha should satisfy two conditions: alpha is greater than 0 and alpha is less than 1. So, 0 less than or equal to alpha less than 1. Now, why are we looking at this? Now, if we write, or if we come to the most basic equation which is given here, from this equation we understand that the forecast for period t plus 1 is a sum of two things, which is a weight associated to the current demand and a weight associated to the current forecast. And because it is a sum of two terms, a weighted sum of two terms, we do not want a negative to come here. We want both of them to contribute, and we do not want a negative term to come here. Therefore, we will not have alpha greater than 1. The moment alpha becomes greater than 1, then we realize that this term starts contributing in a negative manner. Similarly, the moment alpha is less than 0, then this term gives a negative contribution. Since we do not want a negative contribution from either of the terms, we have alpha between 0 and 1. Now, having kind of agreed on the fact that alpha has to be between 0 and 1, now what should be the value of alpha? Should alpha be small or should alpha be large? Now, in this example we have taken alpha is equal to 0.2. So, we have taken alpha as a smaller value and not as a larger value. Now, if we take alpha as a smaller value and start substituting here, we will immediately realize that the weight or the contribution of the demand is actually, if dt and ft are comparable, then the contribution of the demand seems to be less than the contribution of the forecast. If alpha is greater than 0.5, then the contribution of the demand will be more than the contribution of the forecast. Then it actually brings us to another question which says, should not the contribution of demand be more than that of the forecast, which means should alpha be closer to 1 or should alpha be closer to 0. If alpha is small and 0.2, then obviously the contribution of forecast is higher. But if we look at it very carefully, we would want the contribution of forecast to be higher. The whole forecasting comes because this demand is not extremely stable and it exhibits a certain amount of noise. Just for the sake of argument, if all these numbers were 27, then we do not need forecasting and we would say that the next value is 27. So, if the demand is very stable and does not show noise or variation within, in such cases we can have a larger alpha. So long as there is variation and noise, it is advisable to have a smaller value of alpha, which means here we realize that the weight associated with the demand in this term will be less and the forecast will have a higher weight. There is another way of explaining it. If alpha is large here, then what will happen is this F7 will be guided by fewer terms which will contribute to F7. For example, if alpha is 0.8, now this is 0.8, this is 0.16. So, two terms are contributing to a weight of 0.96. So, they have almost contributed to F7. Whereas, if alpha is 0.2, then this is 0.2 and this is 0.16. So, two terms are contributing to a weight of 0.36. So, smaller the alpha, more terms will start contributing to F7. Smaller the alpha, in some sense the weights, even though there are progressively decreasing weights, these will contribute a little more to it, smaller the alpha. Larger the alpha, these the weight associated with these become very, very small. So, if we want all of them to contribute reasonably well, alpha has to be slightly smaller. So, this is how the exponential smoothing model works and is dependent on the alpha and F1, and exponential smoothing provides us with a very good model to forecast the level, where we are able to use all the data, we are able to give progressively decreasing weights to the data as we move past, or progressively increasing weights to more recent data. So, with this we have seen a little bit of forecasting for level or constant data in time series. How to do forecasting when the data exhibits trend, we will see in the next lecture.